In this final section of this chapter, to close things out, we are going to just discuss some different applications of matrices and also discuss another method, our final method actually, of solving a system, and it's called Cramer's Rule. And this is one that a lot of students like because let's be honest, if we're this far along in our math career, we're pretty good at a lot of procedural math, and if you can understand this process, then this is something that can actually solve a system pretty efficiently. It is not necessarily any better or worse than other systems, but if you are pretty good by now at finding the determinant of a matrix, then this could be the method for you. So let's start with a pretty basic example. So the idea here is effectively that we are going to first start off by finding the determinant of this matrix. Okay, so I would encourage you to pause the video and just kind of review these notes here and read through them so you kind of have a heads up as to what we're going to be doing. But I'll just walk you through the steps right now. So the first thing we're going to do is, again, we're going to find the determinant of our matrix, and we're going to call that D for the denominator, and that'll make a little bit more sense in a second. So our D here is going to be the determinant of the matrix here, of this coefficient matrix, I should say. So we're going to draw these straight lines to indicate that we're finding the matrix. So we're going to write 3, 4, 5, 3. So again, we're going to find the determinant here. If you forget how to find the determinant, watch my 7.7 video where I walk us through that process. But effectively, it's going to be, we're going to multiply this diagonal, which is 3 times 3, which is 9. And then I'm going to subtract the product of this diagonal. So let's say minus 20. So our determinant here is negative 11. So our D value is going to be negative 11. Now, next up, we are going to kind of repeat this process, but what we're going to find is something called n sub x, and that's going to be the numerator of our x. And what we're going to do is we're going to take the same matrix, but we are going to now, and let me just use a different color here, we're going to replace our x column. In other words, we're going to replace this x column with our constant column, with these values. So in other words, I'm going to write 1, 9 here, and I'm going to leave the rest of the matrix the same. So I'm replacing, again, my x column with my constant column. And so now I'm going to find the determinant of this matrix. So 1 times 3, which is 3, minus 9 times 4, which is 36, so I get negative 33. All right? Again, just pause for a second, or don't worry too much about what these mean just yet. We'll come back to this. Now, we're going to do n sub y, which is a similar process. We're going to, again, draw our matrix, but this time we're going to replace our y column with our constants. So we're going to copy down 3 and 5. And again, we're going to write down 1, 9 for our y values. And we're going to find the determinant of this matrix. Well, what is this? This is going to be 3 times 9, which is 27, minus 5 times 1, which is 5. And from here, we get 22. So what does Cramer's rule say we do with these values? Well, x is going to be our numerator of x, n sub x here, divided by our determinant, which is why we call it our denominator. So in other words, we get negative 33 over negative 11. So our x value is just equal to 3. What? Yep. It's that easy, right? So now we're going to take n sub y, and we're going to divide it by our d value again. That is going to be 22 over negative 11. Y is equal to negative 2. And so our solution is just 3, negative 2. Now, some of you are already digging this a lot, and some of you are thinking, wait, Mr. No, I could have taken this basic 2x2 system here and solved it using some other method pretty quickly. And I would agree with you. But most of the time, students see the benefit of Cramer's rule, or the reason they appreciate it is when we start dealing with larger systems like this 3x3 here. So let me do this example now. So the first thing I'm going to do with this one is I'm just going to rewrite this first coefficient matrix so we see what we're dealing with. And you don't have to do this, but just so you can see our values lined up pretty cleanly. So there's our coefficient matrix. Our variable matrix is x, y, z. And our constant matrix is 5, 0, negative 1. So we know what we're going to be replacing with. So first, let's find our determinant, so our d value here. Well, when finding the determinant of this coefficient matrix, I said in my previous lesson that you should choose the column or row that's going to be the easiest for you to work with, namely the one that has the most zeros. So I'm going to choose this row right over here. So don't forget the signs, meaning the first one, the first value has to be -4 times, and I'm going to temporarily ignore this column and this row. So then we're going to go ahead and multiply that by -3. Oops, let me just go ahead and write that out. -3 times 2 is -6, minus 6, that's -12. I can skip my 0, okay? I can skip my 0 value because anything multiplied by 0 is 0. And then finally, I'm going to say minus -1. Well, when you subtract a -1, that's adding 1. So plus 1 times whatever. Now, let's just go ahead and ignore this column and that row. So 2 times 6 is 12, minus 6, well, that's just going to be 6. So your determinant is 54. That is going to be our denominator for what we're about to do. Okay, let me go ahead and erase these now. So now let's move on to finding our other determinants. So n sub x here. So n sub x is, again, I'm going to take this coefficient matrix right here. I'm going to take this coefficient matrix and I'm going to replace each column with this constant column. Okay, so since I'm finding n sub x, I'm going to replace my x column with 5, 0, -1. These values are going to go -3, 1, 0, -1, 6, 2. And look at the beauty of this matrix here. The fact that I have zeros down this row here, along this row, make it a great candidate and an easy one for us to find the determinant. So I'm going to say, all right, if I just look at -1, but because of the signs, I'm going to make that +1 times and find 5 times 6, which is 30, minus 3 is 27. So n sub x, should make that clear, n sub x is 27. Okay? So I would encourage you to pause right now and try to see if you can find the other ones on your own. And if you've had a moment to work through it, now let's try the other ones. So n sub y, we're going to replace our y column. So 2, 4, -2. Our y column is going to become 5, 0, -1. And here are the rest, 1, -1, 2. And finding the determinant of this matrix, or this matrix, let's see, let's go with row 2 again. So I'm going to say -4 times 11 plus, since we can skip over the 0, plus 1 times 8, and we get -36. Finally, let's do n sub z, and we're going to bring down 2, 4, -2, -3, 0, and 6. And again, we're going to replace our z column with 5, 0, and -1. Thank you again for those 2 zeros that make my first row here a great candidate for me to find my determinant pretty easily. We're going to say -4 times 3 minus 30, that's -27. And I believe that is 108. So now we're ready to express our solutions. So let's take a look at everything we have here. X is equal to 27, our n sub x, over 54, which is 1/2. Y is equal to -36 over 54. Let's see, these have common factors of 18, so that's -2/3. Z is 108 over 54, and that's going to be 2. So my solution as an ordered triple is 1/2, -2/3, and 2. So again, you can see here that if you are pretty good at finding the determinant and you don't get really flustered with that, then Cramer's rule is a pretty efficient way of solving a 3x3 system here. I want to do one last example with you before we move on to the applications, but let's try something like number 3. Let me do this in a different color and zoom in on this. So for number 3 here, if I start by finding the determinant of this matrix, so let me just write out the matrix first. So we've got 1, -1, 2, and I find the determinant of this. All right, so again, not using brackets, but actually doing these vertical lines here indicate that I'm finding the determinant. And there aren't any zeros, so it doesn't really matter which row you use. I'm just going to go ahead and start with the first row since it's right there. And then that would give me what? 1 times, let's see, that gives me 26 minus 8, that's 18, plus, and I'm going to say plus here because I'm subtracting a negative 1. So plus 1 times, ignore that column and row, that's 13 minus negative 5, so that's positive 18. And then plus 2, which then I would take negative 8 minus 10, that's negative 18. Well, this leads to something interesting. Look at this sum here. What do we get when we add all this up? We get 0. Well, if we get 0, what does that tell us? Well, it tells us two things. One, it tells us that Cramer's rule doesn't work here. Cramer's rule doesn't apply here. We have to use a different method, right? So there's our limitation with Cramer's rule. But what's neat about this is this tells us that our system is dependent. And what's cool about a system that is dependent is that we don't really have to do the row operations. We can just start solving using whatever elimination we want to do until we get a row with 2 variables and set that variable as our independent variable. So again, look back to my videos back in 7.3 or 7.4, which discuss how to solve a system and express a solution with that is dependent.